Good morning, everyone. Once again, welcome to Guru Brahma classes for JE and NEET. So, in this session, we are going to learn about Planck's quantum theory from the chapter Atomic Structure. What are we learning about? Planck's quantum theory, right? So, in this Planck's quantum theory, if you see the phenomena of black body radiation is given by whom? Max Planck. So Max Planck described about black body radiation. His assumptions based on his experiments, what did he assume? He assumed that the absorption or emission of a radiation arises from oscillator, that is atoms in the walls of the black body, right? So already in the previous video we have discussed that what is meant by black body. So black body, what is meant by black body? A perfect absorber and radiator of energy. Perfect absorber and radiator. Radiator is also emitter of radiation of all frequencies. That is called as what? Black body. So there is no ideal black body. Ideal means perfect black body. There is no ideal or perfect black body. Generally, a metallic sphere, hollow sphere. See, this is metallic hollow sphere, which is having a small hole coated with platinum black. Then coated with platinum black can act as nearly black body. It is not ideal, perfect black body, but it behaves as nearly black body. Okay. So that means it can absorb radiation, absorb radiation, and it also can emit radiation or radiate radiation. So it is perfect absorber as well as perfect radiator. So what is responsible for this radiation of energy? He says that this absorption or emission of radiation arises due to oscillator. That means on this wall of this black body, see, it is a metal. Black body is made of metal. This metal contains metallic atoms. So these metallic atoms oscillates, vibrates. Due to that vibration of the atoms in the metal, what is happening? This emission or absorption is happening. Okay. So the radiation, so whatever it is absorbing or radiating, especially, it is radiating energy, and that energy, that radiation possesses a definite amount of energy. So the meaning of that is, so he suggested to Max Planck, atoms and molecules. So this metal is possessing atoms. Here it is atoms, right? So now let us consider this as a black body. it is emitting or absorbing energy only in the form of discrete units. Discrete means isolated or separate units. So for example, let us take it is radiating energy. That radiating energy is not shown like this, not continuous. It is not continuous. It is some discontinuous. Discontinuously, it is radiating energy like this in the form of discrete particles, separate particles. And you find it is not continuous. It is discontinuous. So this body which is radiating energy, let us take it as black body. This black body is radiating energy in the form of small discrete units. Okay, and each unit contains some energy. Okay, and that energy is called as quantum energy. What is that? The amount of energy present in each discrete unit, and that energy is called as a quantum energy. See, it is not in a continuous manner. It is absorbed or emitted discontinuously in the form of small packets of energy or small units called as what? Quantum. So quantum energy. Each unit is associated with quantum energy. Okay. And here each quantum or each unit is possessing how much amount of energy? Quantum energy. And the energy associated with each unit or each packet, that quantum energy is from the experiments of Max Planck. He said that energy associated in each quantum or each discrete unit is directly proportional to its frequency. What is new here? New is frequency of radiation. What is new? Frequency of radiation. Right? He said that energy associated with each quantum or each unit is directly proportional to nu. And removing this proportionality, we are using one proportionality constant called as H. E is equal to H nu. Okay. So what is H here? H is Planck's constant. What is that? Planck's constant. Okay. And the value of Planck's constant is also the value of Planck's constant is calculated as 6.626 into 10 power minus 34 joule into second, not joule per second, it is joule into second. Then when you convert it into SI unit, CGS unit, then what do you get? 6.626 into 10 power minus 34. 1 joule is equal to how much? 10 power minus, and joule is equal to 10 power 7 erg into second. Then what do you get? 6.626 into 10 power minus 34, 7 minus 27 erg into second. Right? So these are the units of what? Planck's constant. So energy, this is for 1 E is equal to H nu is the energy for one discrete unit. What is that called as a quantum energy? Quantum energy. Okay, and here E can be, see, energy is emitted or absorbed in simple integral multiples of quantum. What is the meaning of simple integral multiples of quantum? That means E can be energy. This is one quantum. Two quantum energy means E is equal to 2h nu. E is equal to 3h nu. In this way, integer multiple of h nu. Multiple of h nu. So h nu is quantum. So integral multiples of quantum. Energy radiated or absorbed in the integral multiples of quantum. So 2 into quantum, 1 quantum, 3 into quantum. This way, E is equal to 4 into quantum. In this way, it can. So it cannot be absorbed or radiated in the form of E is equal to 1.5 h nu. This is not possible. Okay, but not in the fractional values. Okay, next Einstein extended this. So Planck's quantum theory was extended by Einstein for all types of electromagnetic radiations. He applied or he extended this Planck's quantum theory for all the types of electromagnetic radiations. So according to Einstein, radiant energy is absorbed or emitted in the form of small particles called as photons. He named that particle as photon. Okay. What Einstein says, for example, this is a body which is radiating energy. This is radiating energy in the form of small packets or small particles, and each particle is named as photon. Simply it is named as photon. Whereas Max Planck did not name it, but here he named it as photon. So the same is applied. Energy associated with one photon, energy of a photon is equal to h nu. This is for how many photons? One photon. Energy for one photon. So energy associated with n number of photons is E is equal to n into h nu. How many photons? N number of photons. Okay. If n is equal to capital Na, what is that? The number of photons are Avogadro number. Then what you write? E is equal to Na into h nu for 1 mole of photons. 1 mole of photons. Right? And 1 mole, already we know that it is 6.023 into 10 power 23. Then E can also be calculated. E is equal to 12375 by lambda, when E energy expressed in electron volts and wavelength expressed in angstrom units. We can use this form. Okay. So hope so this concept is clear. Right? Then let us solve some PYQ JEE mains questions. What are these questions? PYQ JEE main. PYQ JEE main question. So these circled questions are the questions based on Planck's quantum theory. So let us solve question number 1. Right? The energy of 1 mole of photons. Here number of photons given as Avogadro number. That Avogadro number is given as 6.02 into 10 power 23. Okay, per mole. per mole, right? So energy of 1 mole. So we derived the formula E is equal to NH nu. So number of moles, see number of photons is given as Avogadro number N into H into nu is equal to, we know that C is equal to mu lambda, nu is equal to C by lambda, right? So you can write as C by lambda. Then what do you get? Avogadro number given already in the question. Given already in the question. What is that? 6.02 into 10 power 23 per mole into Planck's constant is also given. Okay. Whenever given, only those values for the properties are to be applied. 6.63 into 10 power minus 34 joule into second into C. Velocity of light is also given here. Velocity of light 3 into 10 power 8 meters per second by lambda. So lambda given 300 wavelength. Wavelength given 300 nanometers. 300 into 10 power minus 9 meter by, we know that 1 nanometer is equal to 10 power minus 9 meter. So then what do you get? So the answer given in kilojoule per mole. So we want in kilojoule per mole. So meter cancel, second cancel. So initially we get the answer in joule per mole. Okay, so 399 into 10 power 3, what answer will get? Joule per mole. If we convert it into kilojoule, then what do you get? 399, right? Kilojoule per mole. So the answer is 399 kilojoule per. Okay. So let us go with the next question. Let us see this question number 4. Is that question number 4? Question number 4. So electromagnetic radiation of wavelength is given is just sufficient to ionize the atom of a metal A. So this is atom, for example. This is one atom. Here is the electron. Let us consider this. This is the valence shell. And electromagnetic radiation of wavelength. See, some radiation is given to this, whose wavelength is equal to 663 nanometers. So that this electron came out. So came out means it moved into infinite distance. Moved into infinite distance. So the ionization energy of the metal A. What is asked? Ionization energy. So orally energy. And it is asked in kilojoule per mole. Here given for one atom, we need to calculate per 1 mole. So ionization energy is nothing but energy. We know the formula E is equal to, for 1 mole it is asked, but you can write NHC by lambda, that is equal to Avogadro number. Avogadro number already given in this question. What is that? 6.02 into 10 power 23 per mole into 6.63 into 10 power minus 34 joule into second into 3 into 10 power 8 meters per second by so what is the wavelength given? 663 into 10 power minus 9 meter. So what answer will you get? We'll get 181 into 10 power 3 joule per mole. So if we convert it into kilojoule, 181 kilojoule per mole, right? So that's the answer. Next, coming to the next question. This is the next question, fifth question. Question number 5. Let us see question number 5. A source of monochromatic radiation of wavelength. So there is a source, for example, let us take this as source. It is radiating monochromatic radiation. Monochromatic means of one wavelength, radiation of one wavelength. So the wavelength of this monochromatic radiation is given as 400 nanometers, provides 1000 joules of energy in 10 seconds. When this radiation falls on the surface of the sodium, So this is, let us take sodium. What is this? This is sodium. So from this, radiation is falling on the sodium. (100 joules of per 10 seconds. 100 joules of this energy from the source is falling on the sodium per 10 seconds. So when energy is falling on the sodium, electrons present in the sodium, valence electrons present in the sodium will come out. Okay. What happens? Will come out. Electrons will come out. So how many electrons? See, x into 10 power 20 electrons are ejected per second. We want per seconds. Here the question is given per 10 seconds. 1000 joules per 10 seconds. Then how many joules per 1 second? 100 joules per 1 second. Right? So energy per second falling on the sodium is 100 joules. Assume that the wavelength 400 nanometer is sufficient for ejection. This wavelength 400 nanometers is sufficient for the electron to come out from the sodium. Okay. The value of x is. Okay. We need to calculate the number of electrons. Again, we have the formula E is equal to NHC by lambda. Then if you want to calculate N, you want what? N. N is equal to E lambda by Hc. So energy is 100 joules per second it is asked. So 100 joules into lambda 400 nanometers, 400 into 10 power minus 9 meter by Planck's constant is already given 6.626 into 10 power minus 34 joule into second into C. It's not given, but we need to use 3 into 10 power 8 meters per second. So on calculating it, joule, joule cancel, meter, meter cancel, second, second cancel. There is no unit here, right? Then if you calculate this, what do you get? We get approximately 2.01 into 10 power 20, which is equal to 2 into 10 power 20. So what is asked? X into 10 power 20. So x will be what? 20. X will be, sorry, x is what? 2. Is what? 2. Right? Next, let us solve question number 6. Question number 6. So the number of photon, similar type of question, number of photons emitted by monochromatic single frequency infrared range, finder of power. Power is given. We know that power is equal to work done by time. Then work done is equal to power into time. Work done is also, in other words, you can say it as energy. Energy is equal to power into time. So power given as how much? Power given 1 milliwatts. That means 10 power minus 3 watt into time 0.1 seconds. 10 power minus 1 second. So that is equal to watt into second gives you joule. 10 power minus 4 joule. Right? So energy is 10 power minus 4 joules. You were asked what is asked? The value of x. So the number of photons we are asked, number of photons. We know that for calculating number of photons, E is equal to NHC by lambda. N is equal to E lambda by HC. What is that? E lambda by HC. So N can be calculated as here E. What is E already calculated? 10 power minus 4 joules into lambda. What is lambda? 795. 60 question. Right? So lambda 100 nanometers. 100 into 10 power minus 9 meters by into Planck's constant 6.63 into 10 power minus 34 joule into second into 3 into 10 power 8 meters per second. Okay, joule cancel, second, meter. So what you can get? If you calculate this, you will get the answer as 5 into 10 power 30. So the question asked is x into 10 power 30. So what will be x? X is equal to 5. X is equal to 5. Right? Then let us go with the next question. Is that question number 7? So question number what? 7. A 50 watt bulb emits monochromatic red light of wavelength 795 nanometers. Similar type of questions. The number of photons again asked. Okay. Per 1 second. Per second. You know that energy, work or here energy taken as power into time, that is equal to power how much given, 50 watt into time 1 second, that is equal to 50 joule. So energy is 50 joule, and we know the formula to calculate the number of photons. N is equal to E lambda by Hc. Okay, E lambda by Hc. Energy is equal to 50 joules into lambda given, wavelength given how much, 795 nanometers, 795 into 10 power minus 9 meter. Okay, 10 power minus 9 meter. By H value given here 6.63, 6.63 into 10 power minus 34 joule into second into 3 into 10 power 8 meters per second. So everything gets cancelled, units, and what remains, number of photons, number remains, and what you get, 2 into 10 power 20. So the question is in the format of the asked question is in the format of x into 10 power 20, x into 10 power 20. So the answer will be 2. Okay, so x is equal to what, 2. Next, let us see solve the question number 9. Again, ionization energy is asked. Question number 9 we are speaking. Question number 9. Ionization energy. The ionization energy in kilojoule per mole. What is that? Kilojoule per mole. We know that E is equal to per mole asked. So NHC by lambda. Okay. So number of moles, 1 mole. Per mole is asked, no? In the question per mole it is asked. That means 6.022 into 10 power 23 into, here if you write the units, and what you get, per mole, 1 by mole into H value is not given, 6.626 into 10 power minus 34 joule into second into C. We know that C is 3 into 10 power 8 meters per second by wavelength given 242 nanometers. 242 into 10 power minus 9 meter. So how much energy we are getting? Energy is equal to 494.65 something into 10 power 3 joule per mole we are getting. Okay. Second, meter. So what remains? This joule and mole remains. Okay. Joule and this mole remains. So joule per mole, which is equal to approximately 494.65 gives you 495 10 power 3 kilo joule per mole. The answer will be 495. Okay. So that is with this session we discussed about the concepts of concepts of quantum theory, and after that we have discussed PYQ of JE mains, right? That's all with this session. We shall meet in the next session with another topic. Thank you.